Hello students. This video is going to define the busy Beaver function and get us set up for understanding how it behaves. And the busy Beaver function is what? It relates to Turing machines. Here we're looking at the Morphit Turing machine simulator, and I have it set up with a little Turing machine. The Morphit simulator starts in state 0, so I just jump to the state I want to go to. And this is a little 3-state Turing machine here. It has the start state, the state, the symbol, which in this case that's a blank, that's an I. And then here is the new symbol, the head movement, and the new state. So I'll step through this guy briefly. Here we are in Q0 facing a blank on the Turing machine simulator. And it'll put an I, it'll move left, and we'll go to state Q1. And then here we are in Q1 facing a blank, and it'll put an I, move left, and go to state 2. And one more, and we stop. So this Turing machine put 3 I's onto its tape and halted. Not very interesting, but that's what it did. So a concept to get used to is unary numbers. We can write numbers with only one symbol. Binary numbers have 2 symbols, right? Unary numbers have 1 symbol, and it's just very simple. An empty string is 0, a single symbol is 1, 2 symbols is 2, like that, okay? We can do all this, the same proof without unary numbers. Unary numbers are just easier to think about. So we're going to define the productivity of a Turing machine, as saying we'll start it on a blank tape, we'll run it until it halts, we'll see if it leaves a string of I symbols or whatever symbol you're using, leaves if it sees a unary number on the tape when it's halted, and that's the productivity. Turing machine which runs forever, productivity is 0. If it, in an infinite loop. It leaves other symbols besides the one we were using, productivity is 0. If it leaves gaps, the productivity is 0. Again, we could change these definitions a little bit and come up with the same results, except that if doesn't halt is essential. We need a, we need to spell this correctly, but we need a definitive answer, okay, with the machine giving an answer. So this here, these are our two Turing machines that we're looking at, and we saw over in the simulator here that we had a 3-state machine, and this 3-state machine just very simply wrote 3 I's. From state 0 we go to state 1, go to state 2. Each state we put an I on the tape. And from that we can actually ask ourselves this following question: if I had 3 states to play with, could I do better than 3 I's? The answer is probably, if I did something a little more clever. But we're going to go back to defining these things, and we're going to say the function b, this is the busy Beaver function of n, is the productivity and states one of the symbols a blank. So we'll define this function b of n to be the highest productivity we can achieve with n states and 3 symbols. So for example, b of n is probably greater than or equal to n. easily with end states, like I just demonstrated, I can write an I, move left, do that n times, then halt. That's what this did. So the most productive three-state machine is going to be at least get 3 out of the tape, probably more. Okay, so I'm now going to show you another machine. This machine is a doubling machine. So we'll just start there. And let's say, well, let's put like, 3 eyes or 4 eyes on. Let's put 4 eyes on the tape. You can see how this works. And reset it. And we'll start by going to this doubling machine here. And you can see how it works. Here we are. And I'll step it. That'll make a J. We're going to move left. Then when I get to a blank, I put an I there. I'm going to move right until I find the J. Now you notice the J is moved over 1. And I'm moving to the left until I get a blank spot. What am I going to do? I'm in state Q2, looking at a blank. I'm going to write an I and move right. Go to state 3. State 3, seeing an I, is going to move right until it gets to that J. J goes back to an I. We're in state Q1. We're going to put our marker down over there. State Q2 again. We're going to keep moving left. Okay, you see what this is doing, right? Go right until we get the marker. Put the marker in the next spot. And then eventually we are done. So now we're about to halt. Okay. Okay, so this is going to double a string of I's. So if I have a unary number on the tape, I could use this machine to double the number. And this machine has what? It has 3 states. So over here, if I just, instead of halting, I just went to QD1, okay? Let's start at the beginning. And probably I should go to QD1 over here too, but it doesn't matter. Okay. Let's put a blank tape. And reset. So if I start at the beginning and run this thing, I got 6 I's onto the tape. It wrote 3 I's over here. It doubled them over here. All right. So doubling might be a good way to get more productivity. Like for example, if I wanted to, I could put, I can change this guy over here to go to QD1, right? And then I could take this guy and repeat it, put it down here, right? Now this is great. Instead of QD 1, 2, and 3, this will be QE. QE, okay. Excuse me. So just, rename the states. So now instead of halting over here, I'll go to another copy of the machine. Okay. Got it? So I could, every time I add 3 more states, I could double things. So going back to our notes over here, okay, I could say like this, b of n plus 3 greater than or equal to 2n. Okay. So again, we don't know what's the productivity of, the most clever machine, but I could, double double or double double double. So adding a few more states, double the result again, again, again. So there are clever things we could do that could probably get much better behavior than, one more state gives us one more, okay, productivity output. So that is where we're going to leave it right now, and we'll pick up this discussion in the next video.